Okay guys, so last video of the semester, well hopefully, um, is over subspaces, right? So we've been talking about vector spaces and what a vector space is, and I've been kind of hitting at subspaces. We've talked about subspaces since the beginning of the semester, and since you can think of a subspace as being a smaller space within a larger space, or in this case, a subspace of a vector space, which is a smaller vector space within a larger vector space. Okay, so that's what we want to talk about today. So topics for the day. We're going to be talking about what is a subspace, which I've pretty much said, but mathematically what it is. Two, and then we're going to look at some examples of subspaces. Okay. So definition of a subspace and examples of subspaces. And there's many different ways that you can define a subspace, but we're going to go with the standard definition of a subspace. And then if you have more interest in subspaces, then you can look at different other types of subspaces that you can have for vector spaces. But we're not going to get into that here. We're just going to do like the standard subspace version that the book talks about and go with that. All right. So here we go. Definition. A non-empty subset W, or whatever you want to call it. Remember, we had the vector space V, so we have the subset W, right? Of a vector space V is called a subspace of V if the following properties are true. The first property is that, and again, some books have this and some books don't. I like to have it because I think it's an important property, and it's that the zero vector is in W, right? And it's the same zero vector that is in V, okay? So the zero vector is in W, and this zero vector is the same zero vector that is in my vector space V. 2, if U and V are in W, then U plus V is in W. So essentially, if I add two vectors together, that sum is also in W itself, right? And remember that addition could be a non-standard addition that we dealt with before, or it could be a standard addition. It depends on the vector space we're dealing with. But it's the same addition that the vector space itself has. So U plus V, this addition is coming from the original vector space itself. So W, the smaller subset, does not have a different addition from the larger subset, a larger space. It has the same exact addition. And then 3, if U and V are in W, then C times U is in W. Actually, I don't need V in this case, do I? If U is in W, then C times U is in W. Again, this is the same scalar multiplication, C times U, which could be either standard or non-standard. It depends on the vector space itself. But it's the same scalar multiplication that the vector space V has. So W does not have a different scalar multiplication. It has the same scalar multiplication. So essentially, what we have is that the subset or the subspace is grandfathered in, right? Meaning that whatever the vector space had, okay, whatever the vector space V had in terms of addition and scalar multiplication, the subspace W also has in terms of addition and scalar multiplication. A lot of times what people will say for number 2 is that since when we add U and V together, we get something back in W, we say that it's closed under addition. Closed under addition. And if when we do scalar multiplication, we have C times U, that is back in W, we say that is closed under scalar multiplication. I mean, it's a pretty, when you think about it, it's a pretty straightforward kind of idea, right? Suppose we have a vector space V, right? I'll make this vector space a little bit bigger. So this is my space, okay? And then we have a vector space, a subset that is in V that's a little bit smaller, which is W. Let's say this is outside that. Okay, if we have a vector U and a vector V in W, or we can think about them in terms of points, it doesn't really matter. Okay, we have U and V are in W. Then if I take the sum of U plus V, if I take the sum of U plus V, that sum of U plus V also has to be inside of W. It can't be outside of W. It has to be inside of W if it's a subspace. Okay? And C times U also has to be inside as well, no matter what the scalar is. Okay? So when I do the sum, or if I do a scalar multiplication, that scalar multiplication and that sum is not going to be outside here, but it's going to be inside of my subspace W. It's not going to jump out. That's why we call it closed under addition and closed under scalar multiplication. All right, so a subspace of a vector space and we've said this before many times as well, is a smaller vector space inside of a larger vector space. And we've already said that if when we talked about this before, I have smaller and larger in quotations because we remember that a subspace could be as large as the vector space itself. So, or we can have the smallest subspace, and we talked about that last time, that the zero vector space of V is the smallest subspace of V. Okay. And what's the largest subspace of V? Well, that's going to be V itself. So the vector space V is the largest subspace. So for example, let's talk about R cubed. So suppose V is equal to R cubed. Standard addition and scalar multiplication. Let's just list off the subspaces of R cubed, right? Let's start off with the smallest subspace. And remember, when we talk about the subspace, we have to make sure that the zero vector is in it. So the zero vector in R cubed is equal to 0, 0, 0. Okay. So let's go from the smallest to the largest subspace. Right? I'm just going to kind of just describe them, right? So the smallest one, subspace, is just going to be the point 0, right? Okay, the point 0, 0, 0. Okay. 2. So that's going to be 0 dimensional. First dimension, right? So subspace, we talked about this before, we're going to be the first dimensional, one-dimensional subspaces of R cubed, and those are going to be lines. But we want to make sure that the lines go through the point 0, 0, 0. So the lines going through the origin. Okay. So any line going through the origin will be a subspace. Okay. What about two-dimensional objects? So two-dimensional objects will be planes. So these will be planes going through the origin, right? Or planes containing the origin. Because we want to make sure that 0 is in our subspace. And then last, so that's our two-dimensional objects. And then 4 three-dimensional objects, right? It's just going to be R cubed itself. Okay. So these are all the subspaces of R cubed, at least the way we think about subspaces going by this definition, right? Again, you can expand the idea of subspaces so that the point doesn't have to be the origin, things like that. Where we're not gonna get into that. You can look that up on your own time. But here kind of are the examples of each one of these. Oh, I don't need that. Each one of these subspaces. All right. And here I said that all vectors in the subspace share the same characteristics. Subspace W share the same characteristics. Essentially, they have something that sets them apart from the other elements that are in that vector space. Like, for instance, lines going to the origin, right? So that means that every point on the line has, or every vector on the line has that same direction. Same thing with the planes and things like that, R cubed. All right. Well, very cool. Let's kind of shift gears. I'm looking at, I think I need another sheet here, different sheet. Let's give some examples and determine if something is or is not a subspace. And I think we'll be done. We'll do about 4 examples, and then I think we'll call it a day, right? Is that okay with you guys? Just to make our lives a little bit easier, right, we're going to assume that we have standard addition and scalar multiplication when we do these subspaces. I could have non-standard addition, I could have non-standard scalar multiplication. But that would just make our job harder in determining whether something is a subspace or not. So I'm just going to assume that for all of these problems that we're dealing with, standard addition and standard scalar multiplication. All right? If you want to go home and play with non-standard addition and scalar multiplication, feel free. I'm not gonna do it. All right. So here we go. Determine if the set W is a subspace vector space V. All right, so I'm going to give you one of them. So here's my first one. What? Let V equal R cubed. And let's say that W is going to be equal to the set of all three tuples where I have x1, x2, and 4. So 4 is always our third component, and x1 and x2 could be any real numbers. Again, I'm assuming standard addition and scalar multiplication. If you look at this, right, let's go back to our three properties that have to be true. The zero vector is in W. If U and V are in W, and then U plus V is in W. Then if U is in W, C times U is in W. Now, which one of these properties, is this a subspace? And so if it's a subspace, then all these properties have to be true. Let's look at the first property. Now, remember that this zero vector has to be the same zero vector that we have in R cubed. Well, what is the zero vector in R cubed? So the 0 in W. Well, what's the zero vector in this case for R cubed? Well, the zero vector for R cubed is 0, 0, 0. Okay. The zero vector in R cubed is 0, 0, 0. Is there any way for W to have the zero vector? And the answer is no. The reason why the answer is no is because it has to be 4 in the third component. The closest that this can get to the zero vector, the closest I can get any of my points or vectors in the zero in W to be is 0, 0, 4. So I would say 0, 0, 4 is the closest point to the zero vector. So 0 is not in. The zero vector is not in W. Okay. Maybe that doesn't make you happy though. Maybe you don't like that. What about U plus V? Is U plus V in W? Well, let's look at that one. Let's pick a U. I'll say 1, 2, 4. Let's pick a V. I use 3, 5, 4. Okay. What is U plus V? Well, remember we're using standard addition and scalar multiplication, right? So that means U plus V, I'm just going to do regular addition, so I get 4, 7, and 8. This is a problem, right? Because what should be in this third component? This third component should be a 4. Right? So U plus V is not in W. What about C times U? Is C times U in W? What do you guys think? If you've been saying C times U can't be in W either, you're absolutely right. Let me erase this. I'm going to get rid of my subspace definition. Remember, we're still using standard addition. Okay, let me pick a C real quick. Let's look at C, 4. Why not? 4 times 3, 8, 4. Let's use 7. Why not? For my C. Okay. When I multiply this using regular addition, regular scalar multiplication, standard scalar multiplication, I get 21, 24, 28. This should be a 4. So that means that C times U is also not in W. I mean, it's in W if C is equal to 1, but That's just one C out of infinite values of C I could have chosen. C times U is not in W. So I have three reasons why this is not a subspace. First, the zero vector is not in W. Second, U plus V is not in W. Third, C times U is not in W. And this is triply bad, so W is not a subspace of V. Okay. W is not subspace of V. Let's look at another one. Let's look at 2. Let V equal M33. These are matrices of size 3 by 3, and W equal D33. These are diagonal matrices of size 3 by 3. I'm going to say that. Diagonal matrices of size 3 by 3. Okay. I want to know is W a subspace? Again, we're assuming standard addition and scalar multiplication. So I want to know, is W a subspace of V? Right? That's what I want to know. Well, let's look at all of the properties here, right? 1, 2, and 3. See if any of these fail. 1. It's a zero vector in W. Now, it has to be the same zero vector that is in V. What is a zero vector in V? What's a zero vector all matrices of size 3 by 3? Well, it's going to be a 3 by 3 matrix with all zeros, right? But guess what? This matrix is also a diagonal matrix. Like I said, the zero vector is a diagonal matrix of size 3 by 3.